just tap anywhere else besides there.
Okay, I think they can hear
There
us.
you go. All right, here we go. It's on.
Oops.
What?
I only connected to her Apple Pencil.
Click disconnect. Okay.
Disconnect.
So 1.5, infinite limits. So a limit in which f of x increases or decreases without bound as x approaches some number c is called an infinite limit. Now, when we've had it approach infinity, what do we say is our ultimate overall limit? Does not exist. That's still true, but today we're going to actually kind of investigate what kind of infinity we're approaching. Is it positive infinity or negative infinity? The answer is still ultimately does not exist, but we are going to give answers in terms of infinity today to talk about what kind of infinite limit we might have. So it says the statements that the limit as x approaches c of f of x equals positive infinity and the limit as x approaches c of f of x equals negative infinity do not mean that the limit exists. They tell you that the limit fails to exist by denoting unbounded behavior. So when you see infinity and negative infinity, we're still interpreting that as does not exist. We're just going to give kind of a slightly more specific does not exist answer, as in positive infinity or negative infinity. But it still means there is no limit. And so in this one, we've got one going positive and one going negative, which we know is kind of the double whammy of different left and right limits, and they're both unbounded. Okay, so we're going to talk about how infinite are these limits and which way do they go. That is frozen. Oh, it says freeze. I don't know why I did that. Here we go. All right, so it says determine the limit of each function. We're going to look at example A first. So, and I should tell you that I'm supposed to have this say as x approaches 1, but I didn't. So we're going to pick 1. And the reason I'm picking 1 is because 1 is where this is a problem, right? If I do direct substitution and plug 1 in, what do I get in the bottom?
0.
0. So normally we would just straight up say does not exist, right? But we're going to talk about how infinite that is. So let's imagine if plugging in some number that's really close to 1, like really close to 1, like closer than that.
Like 0.999.
Yeah, like 0.9999, okay? If I do 0.9999 minus 1, how many 9 did I do? 4? 9999. I get some kind of scientific notation, tiny number, and then I'm supposed to square it. And I get an even smaller tiny scientific notation. 1 times 10 to the negative 8th. What does that mean? What's 1 times 10 to the negative 8th? That's 0.000000001. So, yes. So what I'm saying is we get a very small number underneath as our denominator, yes? So, when x approaches 1, I'm going to use the x arrow 1 to abbreviate that, from the left, or the right, wouldn't the same, it'd be the same if I did the other way, if I did 1.11111 or 00001, wouldn't I get a number that is also really small? Because it's going to be the same thing when we square it, right, as if I did 0.9999. So, because it's being squared. The x minus 1 squared is very small, right? The closer I get to 1, doesn't it get even smaller?
What does it mean from the left on the right?
Or, I said or, left or right. X minus 1 squared is very small. So what happens when I divide 1 by a very small number?
It's a big number.
It's really big, right? If I divide 1 by a really tiny number, doesn't it make it ultimately bigger? We're talking about the number of times that number fits in. Think about the number like fraction like 1/8. I'm taking 1 and dividing it into 8 pieces, right? But if I do like 1 divided by 100, right? When you divide by a very, very small number, you get a really, really large positive number. So, if we do, so we're going to say, so the quotient (1 over x minus 1 squared) is a large positive, because of the square, number as x approaches 1 from either side. So the limit as x approaches 1 of 1 over x minus 1 squared is positive infinity, which still means does not exist. We're just being more specific about it. And like if you're not sure, divide 1 by a really, really small decimal. 1 divided by, what did we get? 1, what did we say? It was 0.00, like to the 8th power, 1, 2, 3, 4, 5, 6, 7, 8. I get 100 million, right? 1 divided by that really tiny decimal is 100 million. So you get so if you're not sure what's going to happen, just make a number up and test it, right? See what you get. Okay. So that one was positive infinity, primarily because we were always going to get a positive number, right? When I go to square whatever's underneath, it's always going to be positive. But that may not always be the case, so let's look at a different kind. So we have negative 1 over x minus 1 here in example B. So let's just think about what happens when we plug in. And this is going to be different, right? We're not going to get the same thing from the left or the right because it's not being squared. So think about what happens if I plug in a number that's really, really close to 1 less than 1. So like let's do the 0.9999 again, right? You get, yeah, you get a very small negative number on the bottom, but a negative divided by a negative is a positive, and it's going to turn into a really big positive number, right? And then what happens if you plug it in from the other side, from the right-hand side, like a 1.0001, you're going to get a really big negative number. So from the left side, we're going to approach positive infinity, and from the right side, we're going to approach negative infinity. So we're just going to write that out. Again, anytime we're doing this description, however you want to write it is up to you. So from the left, when x approaches 1, x minus 1 is a small negative. So the quotient is a large negative.
Wouldn't it be a large positive?
Oh, yep, sorry. Positive. Small positive. Large positive. And from the right, it's the opposite. So when x approaches 1, x minus 1 is a small negative. I don't know why I wrote out the word positive. Small negative, and the quotient is a large negative.
Do you need to write this part out too, or can you just write the limits?
At this point, I mean, you could maybe abbreviate the second one. So like, you could say like, on the other side, we've only done one limit otherwise. So right now, I'm just practicing writing it out. So.
Wouldn't the one from the right at the bottom be a small positive?
No, the one from the right is going to be a small negative because you're getting negative 1 on top, and you're going to have a positive number on the bottom when you do something like 1.0001 minus 1. So you're going to have a negative over a positive. So from the right, it'll be a negative as well. So it'll be positive from the left and negative from the right. It's like, if I did...
Or like just the bottom half.
from the right, when x approaches 1, x minus 1 is a small negative, and the quotient is a large negative. Will be when you plug it in.
Wait, I don't know what I even asked really, but when you do like 1 minus, yeah, the bottom would be positive.
And the top is negative.
Yeah.
Oh,
Okay,
I see
that
what you're
says a
saying.
small
Got it. A
negative.
small, yeah, okay, is a small positive. Sorry.
Okay.
I see what you're saying. Got it. I got it. Is a small, and this one would be a small negative. So I was right when I wrote negative on this one the first time. Okay, hold on. I just did that because I did the opposite up here. But this is a small negative as well.
These people are going to be very confused.
I know they are. It's because I got corrected when I wasn't wrong the first time. Okay, so when x approaches 1, x minus 1 is a small negative from the left, right? So a negative divided by negative gives us a positive number overall. And then on the second part, you get a small positive, and the quotient overall is a large negative. Okay, there we go. Now we have it. And so the limits, which maybe are the clearest of them all, as we approach 1 from the left, I'm just going to write g of x. We get a positive infinity. That's going to be our large positive. And we approach it from the right. We get a large negative, so negative infinity. Still DNE overall, right? Good. Okay. So when we have unbounded graphs, we typically have asymptotes, right? Isn't that why it's usually unbounded? It's approaching the asymptote. So when we're discussing infinite limits, it is helpful if we also discuss asymptotes. So if f of x approaches infinity or negative infinity as x approaches c from the right to the left, then the line x equals c, wherever c is at, is going to be where your vertical asymptote is at, right? So we have a little theorem here, 1.14, says that if f and g are continuous on an open interval that contains the point c, and then it says if f of c is not equal to 0 and g of c is equal to 0, there exists an open interval containing c such that g of x, whatever, here we go. There's all that stuff. They're essentially saying if you have two functions being divided by each other, g of x is your denominator function, right? Which is why they're saying that, you know, when g of c equals 0, then there exists essentially an asymptote, right? And there's an asymptote at whatever x equals c is, where you're taking that limit. So, it says determine all vertical asymptotes of the graph of each function. This is more algebra-like. So where will the asymptote live in example A? What are we going to do to try to figure out where the asymptote is? Essentially, the definition
Can I
says.
know what x is not existent at?
Yeah. So
Yeah,
we're.
so negative.
So set it.
So you're going to set the denominator equal to 0 is what I was
Yeah,
hoping we were going to get
sorry.
to. So 2 times x plus 1 has to be 0, right? Does that make sense? Why that has to be the case. And technically the 2 doesn't even matter because it's not even connected to the x, but I'll put it there. But if we divide the 2 away, x plus 1 has to be equal to 0 for us to have an asymptote. So the asymptote must be at
-1.
-1. There it is. That's it.
Yay. Oh wow, I can do this.
So surprised.
You do have to check. You did the thing. You do have to check with the numerator because what happens sometimes you create a hole if it's replicated in the numerator, or like if you could create a 0 that would disappear, right? And so like this one's good because the numerator's just 1. But like if there was a place where the numerator would match, then we have to think about that, which we will talk about here in a second. Okay. So let's talk about the next one. Look at the denominator. X squared minus 1.
Positive and negative.
Yeah, and you could do that one of two ways. We could dots it, right? X plus 1, x minus 1. Or can you just solve it with square roots as long as you don't forget the plus or minus, right? So we get positive 1 and negative 1. Now you do need to check because we do have a numerator with a variable. But is there any way to get 1 or negative 1 as an answer there? No. In theory. I mean, is there a way to get like the same factor, x minus 1, x plus 1?
Yes.
No. I don't think we can't make 0 up there at all, can we? Would it be possible to get a 0 on the top? Essentially, is what we need to figure out.
No.
Because it's x
Yeah.
squared plus 1, you're adding to it. If it was x squared minus 1, we could talk about it, right? Because then they'd be the same. But because it's plus 1, if you plug in, say, a 0, you're going to get 0 plus 1, still going to be positive. If you plug in a negative 1, you're going to 1. 1 plus 1 is positive 2, right? So x equals 1 and x equals negative 1 are both asymptotes. And I am going to make a little note here just so that you would think to check that.
Can you say x equals positive or negative 1?
Yeah, you can.
Okay.
And so, since the numerator is not 0 at either point, they are both asymptotes. But you do need to check. Because if they're not asymptotes, they're a hole, and that wouldn't count, right? It wouldn't go to infinity if it was a hole. It could potentially still have a limit.
What did you check? Like, what? Did you just plug those in the top?
I was trying to figure out if there was a way to make this equal to 0 and figure, like you would factor the top 2 if you could, but it doesn't, right? Because if I go to try to solve this, I can't, right?
'Cause they would cancel.
Yeah, there's literally no way to get 0 out of the numerator, so that means there's no way they could be the same.
Okay.
Ultimately, I was just checking to see if I could factor the numerator to be the same, right? The rule is if you can make the same thing in the numerator and the denominator, it cancels out to be a whole instead of an asymptote. Okay? Cotangent of x is going to be easier to think about in terms of cosine and sine. So you do is 1 over tangent, but think about, turn it to cosine and sine for me. Yeah, isn't it cosine over sine?
Yeah.
And the reason that that's easier is because then I just need to know, to find an asymptote, don't I need to know where sine of x is equal to 0? So you're going to ask yourself, where is sine of x equal to 0, and that's going to be your asymptotes.
0.
Yep, and then where else? Where doesn't it repeat?
2, I mean pi, just pi.
Oops, not close. So, yep, 0 and pi and 2 pi and negative 2 pi. So how do I write that?
Pi x.
Yeah, so you do like 0 plus
Yeah.
pi n, or do I need the 0?
No.
So really you could just say pi n or n pi.
Yeah.
So there are infinitely many asymptotes at x equals pi n. I'm not going to write it that way, just so we have that note in our notes. There are infinitely many. You could just write it as pi n. It's assumed there, but... Okay. Determine all vertical asymptotes of the graph of f of x. In order to do this, we'll need to factor. And we should factor both parts to check for holes. So how can we factor the top? Yeah, so we'd have x plus 4 and x minus 2, or whatever order you prefer. And then x squared minus 4 is a dot, so that's x plus 2x minus 2.
So then do you like cancel?
Yes, so as far as considering asymptotes, the x minus 2 and x minus 2 cancels, and that's a whole, not an asymptote, right? So it's not going to be infinite there. So we don't have to worry about that part. All we care about then is that there's a vertical asymptote where?
Negative
Yes.
2.
So we have a vertical asymptote at x equals negative 2. There is a hole at positive 2, but it's not an asymptote. So we would not have an unbounded limit at positive 2, only at negative 2. Okay, so let's take a look at this guy. They've asked us to find two limits, the left limit and the right limit of the same function. And I'm just going to kind of rewrite this function so that it's in factored format as x times x minus 3 over x minus 1, just so I can check to see if anything cancels out. Does anything cancel out? No. So that means I have a vertical asymptote where?
At 1.
Yes. Which ultimately means what for the limit at 1? It's going to have to be some kind of infinite limit, right? Because there's a vertical asymptote there. We just have to figure out if it's positive or negative. What's the matter?
I don't understand like the sentence that just came out of your mouth. Like,
So there's a vertical asymptote at x equals 1, which means when we're looking at the limits as x approaches 1, it has to be unbounded, either positive infinity or negative infinity, because that's what happens at an asymptote. Right? Isn't the whole point of an asymptote your dashed line? That you have a function that either goes like this towards it or goes like this towards it. So your limit has to be unbounded. So verifying that we have an asymptote at a certain location helps us determine what kind of limit to be looking for.
I see. Okay.
We just have to figure out if they're the same or different, if it's positive infinity or negative infinity, if they is what they're looking for here. Okay, so let's start with the left limit, because that's what's listed first. So I think the best way to approach this problem is to just plug a number in that's coming from the left and see what you get. It will give you a really good idea of what to expect for your function. So let's pick a number to the left of 1 to plug in.
Negative 1.
Well, you remember you want to be as close to 1 as you can get though, for it to be accurate.
So we don't.
Yeah, 0.999.
Yeah, something with some 9s that are really close to 1, right? I don't care how many you go with, do a couple at least, but you want to get closest to 1, or it won't be very big and you'll think that you maybe did it wrong. So go ahead and plug it in and see what you get. If you plug in 0.999, well, let's say, squared minus 3 times 0.999, and then divide that by 0.999 minus 1 in parentheses, of course. You should get a really big, a biggish number. It's not huge yet, but what, anybody do it?
Yeah.
What'd you get?
1998.
Yeah.
Almost 19.
Yeah, like 1,000.
1,099.
Yeah, almost 1,999. What's going to happen as I get further, it's just going to keep adding a digit, right? And so the key is it was a positive big number. So what are we going to say is our limit?
Positive infinity.
Positive infinity for the left limit. And then we're going to do the same thing from the right, but we'll pick a different number because it's got to come from the right side, but something
1.001.
great. Plug in 1.001. Minus the p. And then divide that by 1 minus 1. And it's possible that you get another positive, right? They could both be going up, but this one happens to be
Negative.
a negative big number. I get negative 2,000.999. So it's a negative infinity. I will say some people like to try to plug this in and just look at the graph, which I can appreciate to a certain degree, but sometimes a graph has really a big deal of trouble with asymptotes, and it makes the graph look kind of funny. You can't necessarily tell the asymptote's there, but sometimes, especially if they're both going up or both going down, it kind of looks like the graph connects because the graphing calculator tries to draw the asymptote. So I would always verify by actually plugging a value in to check if you're not exactly sure what's happening, because calculators have a difficult time dealing with asymptotes depending on how close you're getting to that number. Okay. So we have just a few properties of infinite limits that we can talk about. Similar to properties that we've done before. So they're letting C and L be real numbers, C being the number x is approaching, L being the limit. And f and g are functions such that the limit as we're approaching c for f of x is positive infinity, and the limit as x approaches c of g of x is L. So we have one limit that we can find and one that's unbounded, is what they're saying using these two limits. So one thing they're saying is if we add or subtract a limit that's infinite with a limit that's real, right? Imagine me doing let's say my limit is 5. Infinity plus 5 is really just more infinity, right? So number one is saying it's just getting closer to infinity, right? If it was negative infinity plus 5, minus 5, it would be negative infinity, right? So some are difference of an infinite limit with a regular limit, or a real limit, still infinity. The product is saying that if you take the multiplied together, you're either going to get positive infinity or negative infinity. I wonder if that's not a typo. If those are backwards. L is positive. Yeah, that's for sure backwards.
Dang it.
I'm going to double check in case I'm not using my brain correctly, but those are for sure backwards.
Dang, feel bad for the people watching these notes.
Oh yeah, because I just copied these backwards. That's hilarious. Okay, no, it's not.
Oh.
Here, just do this. Do positive infinity and negative infinity, and then it's all fixed. Okay. It's fine. It makes more sense this way. Doesn't it make sense if I take infinity times a positive limit, I would get a positive answer? And if I take infinity times a negative limit, I would get a negative infinity answer? Yeah. And then take a look at this quotient. F of x is your your infinity. And this is your limit L. So before we've been dividing by small numbers, we haven't talked about what happens when you divide by a big number. So if I take a constant number and divide it by increasingly bigger numbers, I'm going to get closer and closer and closer to 0, right? Because it's getting smaller and smaller and smaller. If you're not sure, test it out. If I take 5 and divide by 1,000, right, I get 0.005. If I take 5 divided by 100,000, I get 5 times 10 to the negative fifth, a much smaller number, right? It's just going to get smaller and smaller and smaller, closer to 0. Is it ever going to actually really get to 0? No. But it's approaching, right? That's what a limit is. It's approaching 0. So if you divide a regular number by a really big number, it's 0. Even if it's positive or negative, we're going towards 0. So we're going to apply those properties. Determine the following limits. The limit as x approaches 0 of 1 plus 1 over x squared. So this would be a case where I'd maybe break this up. Remember how we learned that we can separate limits, right? The limit as x approaches 0 of 1, plus I could then do the limit as x approaches 0 of 1 over x squared. Just break it up into two limits. So let's think about what that would be. What's the limit as x approaches 0 of 1? 1. What's the limit as x approaches 0 of 1 over x squared? If I get closer and closer and closer to 0, I'd be dividing by really, really small numbers. What if I divide 1 by really, really small numbers? What do I get?
DNE, but then
Yeah.
it would be.
We're going to go ahead and talk about in terms of infinity. So
It gets infinity.
You can't just plug in 0 then?
no, because 1 over 0 is undefined, right? And we want to give an actual infinite limit. So this goes back to what we were talking about earlier today. If I put in like 0.00001 squared and I divide 1 by a really small number, we learned we get a really big number. So this is going to approach positive infinity because it's squared, right? X squared would always be positive. Well, what's 1 plus infinity for the property we just talked about?
Infinity and 1.
Infinity, there it is. That's what I was looking for.
Dang, that's nice.
Wait, how did you know that it was positive infinity now?
Because if you plug a number in and square it, no matter if it's positive or negative, you're always going to get a positive answer. Okay. To continue my really good notes today, this cosine's supposed to be a cotangent, so just go ahead and.
Man.
Really batting 1,000 today, aren't I? Whoops.
It's going great.
Okay, and this time we're just doing a left limit. Do you guys see that? It's 1 minus there. So we're thinking about numbers that are coming to 1 from the left side, so like 0.9999, right? So what's going to happen on top if I plug in, let's just talk about the numerator. The limit as x approaches 1 from the left of just x squared plus 1. Let's talk about that. What's that going to be? What happens if I plug 1 in? I can plug 1 in here because it's not going to be undefined. Aren't I going to get 2? Right? I'm approaching 2. Okay, so then let's talk about the bottom part. The limit as x approaches 1 from the left of cotangent of pi x. Who remembers what the cotangent graph looks like? Anybody?
It's
Yeah.
It's weird.
The cotangent graph.
It's ugly.
Yeah, it goes this way. Yes. Do we happen to remember where the asymptotes are for cotangent?
Pi over 4.
Not pi over 4.
pi over 2.
Pi over 2 is for tangent.
Dang it.
So pi, multiples of pi. So like 0 and pi. How would we figure that out if we didn't happen to remember it? Our handy dandy unit circle,
I was gonna say
right? So cotangent is what? Cosine over sine. So where would we figure out cotangent's undefined at? By figuring out where sine is 0, which we talked about earlier, right? We did cotangent earlier. And we decided it was 0 at 0 and pi, remember the pi and asymptotes, right? And so then what we need to figure out is what's happening as we approach it from the left. So look, I just kind of did a little sketch here. What are we going towards as we come at?
negative and
Right? Because if I plug 1 here, aren't I going towards pi? Right? So I'm going. That's why I'm picking pi because there's a pi x in here. If this was just x, we'd be at 0, right? Or 1 technically, but that would be boring because that would be an actual value. So here we're going towards pi, and so but it's going negative, right? So wouldn't we say negative infinity? Right? Because it's tracing toward.
But it's 2 over.
Yeah, I'm not done. We're not done yet. So I'm just doing the limit of cotangent pi x right now, which is going to be negative infinity. So then when we go to do the limit, as x approaches 1 from the left of the whole thing, so x squared plus 1 over cotangent pi x, you're going to have 2 over negative infinity. And what did our property up here say happened if you had a number divided by an infinity?
0.
0. You need to make a note, that's per property 3 from the box up above.
So anything that's dividing is automatically just going to be 0,
Well,
technically, or
Dividing by an infinity will be
Yeah,
0.
okay.
Yes, if
Okay.
you have a regular number on top, any kind of real number on top.
like, will that happen?
That'd be infinity still,
Okay.
right? If you do, it would still be infinity.
It's, I
Because
guess.
infinity goes on for forever, so even if you divide and make it smaller, it's still going to get bigger.
Okay. I guess you're right.
Okay, well, you really made me think about that. Sorry. I don't know, hold on. Alright, so we got one more. We're going to take 0 from the right of 3 cotangent of x. So here we just, again, have to think about, with 3, that's going to go in front of it. We've got 3 times whatever our limit is. So if you wanted to separate these as a product, you could do the limit as x approaches 0 from the right of 3 is 3. And then we need to do the limit as x approaches 0 from the right of cotangent x. And I'm going to just revert back to my cotangent graph up here. We're approaching 0 from the right.
So infinity.
Do we see it?
Yeah.
0 from the right is going to be positive infinity.
Yeah.
If I trace this over here, just so we see it,
Yeah.
going towards 0 from the right-hand side, going to be going towards positive infinity. So this is a product, so we're going to multiply those two limits together. So the limit as x approaches 0 from the right of 3 cotangent x is going to be 3 times infinity, which is just more infinity. I'm done.
Dang.
Stop recording.
Okay.
Cut the camera.
The camera. I feel like I need to draw the cotangent
Okay,
graph.
Yeah, draw the cotangent graph for that. Oh man,
For
yeah, that would've been nice
reference.
for them to have sooner, sorry.
Here's
Yeah, Sarah.
here's the cotangent graph.
Yeah.
So when on the, just since I'm not gonna be doing well, when do we have to do the writing stuff?
I'll probably ask you to describe. I'm just doing it for the notes here.
Okay, bye guys.